Hey, you guys. We are going to continue. We only have a couple new lessons left. Yay, is probably what most of you are thinking. If you want to log into Agile Mind, go to My Courses, Unit 8 on the left, Topic 23. Out of 22 now, we're on to 23. Down arrow next to 23, down arrow next to lessons. We are on lesson 3, polynomial products. And I will talk about what those words, well, polynomial, you probably don't know, but products, is the answer to a multiplication problem. So we'll talk about what polynomial means today. I won't really be using Agile Mind slides, but again, you are welcome to go through those. They have some great information. We are going to be in your workbook. We are going to start on page 326. Page 326. You may want to grab a calculator also. I'm going to flip around this camera and we will get started. So as you all know, we have been talking about quadratics. We have been talking about equations that have a highest exponent of 2. But what we haven't really spent a whole lot of time doing is figuring out where does that x squared come from. We know that when we combine like terms, and I'm just going to make something really just random here. If I combine like terms, like if I have 2x, see if my pen will work here, 2x plus 3 plus, let's say, 4x minus 6. If I was to add these, that means looking for like terms, so same variable and same exponent. So we have 2x plus 4x is 6x, and 3 and negative 6. Put those together, 3 minus 6 is negative 3. Adding like terms, notice nothing changed. I started with x's, I end with x's. You can think of adding and subtracting as just counting up how many do I have. So where is it that we get an x squared from? How do we even get something that is quadratic, something that makes this U-shaped parabola in the first place? Because everything we've seen so far, combining like terms, again, the variable doesn't change. So it can't be from adding or subtracting that we get that x squared. Instead, like we saw with the title of this lesson, products, it comes from multiplication. So the good news is that multiplication of variable terms is not terrible. The good news also is that there's a really, really easy way to keep your multiplication organized, and that is using what is referred to as either the area model, or you'll hear a lot of your math teachers in future years say box method multiplication. The cool part about box, again, is it keeps all of your multiplication organized. For those of you who've been through biology, this looks an awful lot like those Punnett squares you used in biology. So before we even start multiplying with variables, we're going to do 2 examples where we just multiply with numbers to show you why this area model or box method actually works. So I'm going to actually start with number 3 on page 326. If I look in these parentheses, I have 10 plus 8, which is 18, times, because I see that dot right there in the middle, 10 plus 7, which is 17. So what I want you to do is go to your calculator, and I want you to go ahead and multiply 18 times 17. So I'm going to go to mine. I'm going to do 18, not 118, 18 times 17, and we can see that we get 306. 18 times 17 is 306. Now, I realize if you're going to have to multiply 18 plus 17, yes, most of you are just going to go to your calculator and you are going to multiply. But again, the reason I'm showing you this example and one more is to show you why this box method or area model actually works. So as you saw, the problem actually spread out, if you will, the 18 in the 17. They took the ones place, the 8, and the 7, and separated it from the tens place, a 10. So I'm going to take what's in each of these parentheses, and I'm going to separate them across the top and the side of my box. So I had 10 plus 8 to represent the 18, and 10 plus 7 to represent the 17. Now, does it really matter which set of parentheses goes across the top and which set goes across the side? No, as long as you keep what's in one set of parentheses completely on one side and what's in the other set of parentheses completely on the other. So, and again, for those of you who are familiar with Punnett squares from biology, you'll understand how this multiplication works. But for the rest of you, here we go. In this first box, I see I have a 10 above the box and I have a 10 to the left of the box. So I'm going to multiply those. 10 times 10 is 100. Moving over to this box, I have 10 times 8, which is 80. Moving down, I have 7 times 8, which is 56. And I have 7 times 10, which is 70. So does that mean 18 times 17 is all these numbers? No. Now that I have done these groups of multiplication, I am going to add up everything that is left. 10 plus 80 plus 70 plus 56. Now, because I'm not using a calculator, if you're using a calculator, type it in. Because I'm not using one, I'm going to do multiplication or addition that stands out to me first. 80 plus 70 is 150. 150 plus 100 is 250. And 250 plus 56 is 306. Look at that. I got the same answer. Is this the most straightforward way to multiply 18 times 17? Absolutely not. But it does show you that breaking apart multiple terms and multiplying them in smaller pieces that might be easier to do if you don't have a calculator. This is really easy mental math, but breaking up that term that you are multiplying, you can break it apart into smaller pieces and you still get that same product, that same answer to multiplication. So if I look down, I'll do one more example kind of like this before we move into actually dealing with variables and seeing where that x squared comes from. So we have 20 plus 8, which is, of course, 28. And 20 plus 7, which is 27. So we have 28 times 27. And I'm going to just check what that is right here so we know that we got the right answer. 756. I'm going to write that down. But just again, showing you why this area model or this box method, how it works or why it works, that 28 was separated again, the ones place and the tens place, and the ones place and the tens place for the 27. So as long as I keep what's in each parenthesis on its own side, it doesn't really matter what side it goes on. So I'm going to separate it this way this time, 20 plus 8, and the other parenthesis, 20 plus 7. And I'm going to use my multiplication to fill it in. So 20 times 20 is 400. And it doesn't really matter. You notice this time I went, kind of clockwise. It does not matter what order you go to fill in this box. So I'm going to go in a different order this time. 20 times 8 is 160. 20 times 7 is 140. And 8 times 7 is 56. Again, I can't say that I have 4 different answers for multiplying. I'm going to take all those terms inside of my parentheses, or inside of my box, and I'm going to add them together. And again, since I'm not working with a calculator, I'm going to add in the way that makes most sense to me because order of addition does not matter. 140 plus 160 is 300. 300 plus 400 is 700. And 700 plus 56 is 756. And look, we got that same answer. So it's a really nice visual to see that this box method or this area model of multiplication works, because once we start throwing in variables, we can't actually do x plus 8 and say, oh, I know that's equal to insert number or letter. We can't actually add these pieces together because they are not like terms. An x and an 8 cannot be combined. So the only way we can multiply, and I know this is multiplication because of that times dot right here, the only way we can multiply is using this same idea of this box method or area model. So I'm going to take one of my parentheses and put it across the top, x plus 8, and I'm going to put my other parenthesis and put it down the side, x plus 7. And again, like I said before, to fill in these boxes with our multiplication, the order in which you multiply does not matter at all. So I'm actually going to start in the easiest spot. I'm going to start in that bottom right corner. So 7 times 8, we like a lot of 7 times 8s today. 7 times 8 is 56. I'm going to move over here. 7 times x. Well, 7 times an x, I can't multiply them and call them a new number or new letter, so I just write them next to each other. 7x. Similarly, up here in the top right corner, we have 8 times x, which is 8x. And here is where that x squared comes from. We know, like I did with that example on the bottom, just simply adding variables does not change any exponents. It's multiplying that does. X times x is x squared. Multiplying two x's together is what creates that quadratic, that exponent of 2. So just like we did with the area model, with these area model or box method problems in 3 and 4, we're not going to leave just numbers inside the box. We're going to take them out and we're going to add them together as much as possible. Now, obviously, our addition looks a little bit different than it did in number 3 and 4, and that's because we have variables. But keep in mind what you already know. If I'm going to add variables, then we have to look for like terms. We need to look for same variable and same exponent. So the only place that I see lots of x's, but the only place I see same letter and same exponent is that 8x plus 7x, which is 15x. So then what do I do with these other pieces? Well, I bring them down. They're still part of my multiplication, so they still need to be part of my final answer, bringing down the x squared and the plus 56 at the end. And there you go. We just multiplied these two sets of terms together. Now, going with that, it's tough sometimes to say, hey, I multiplied these sets of terms. So that's where the word polynomial comes from. Polynomial, I'm going to write this down here at the bottom. It's just a good math word to know. Polynomial. Poly is a prefix you may have heard in some, in pre-algebra, 7th, 8th grade math. Poly is a prefix that means many. Polynomial literally means many terms. And terms in math are separated. There are variables. They can have a number and a variable together. They can have an exponent. Terms specifically are separated. Terms are separated by plus and minus signs. Separated by plus and minus signs. So in math, anytime I have something like that x plus 8 or that x plus 7 that we just had in number 5, x plus 8 is 2 terms inside of this parenthesis because the x is separated from the 8 by a plus, and the x and the 7 is another set of 2 terms because they are separated by a plus sign. So I have polynomials that I am multiplying. Now you will find that in math classes, you end up multiplying or you end up dealing with certain numbers of terms, certain numbers of terms in a polynomial more often than others. Like you often deal with 1 term or 2 terms or 3 terms. So they have special names that we're going to look at here in a second. So we'll come back to that. We'll come back to that vocab. Something else I want to show you. This box method, this area method is really honestly what I'm going to focus on for all of our multiplication. But I want to show you one other thing that your teachers in future years might tell you or show you or use in class. They may say, go ahead and multiply these guys using the distributive property or using FOIL. Now, specifically, FOIL only works when you have 2 terms by 2 terms. So like we had already said, x plus 8, there's 2 terms, x plus 7, there's 2 terms. FOIL specifically only works for 2 terms. So what does FOIL represent, or what does FOIL stand for? FOIL means first. Multiply the first terms in each set of parentheses. So I have my x times x, which is x squared. The O in FOIL means outer or outside. Multiply the outermost terms together. So that would be our x times 7, which is 7x. I stands for inner or inside. Multiply the innermost terms. So that would be our 8 times x, which is 8x. And L, if F is first, L stands for last. Multiply the last term in each parenthesis, which would be our 7 times 8, which is 56. And if you recognize that problem in number 6 is exactly the same problem as number 5, and you'll notice these 4 terms that we have here are the same 4 terms that we had from inside of our box. So I know that when I look to add as much as possible, 7x plus 8x, I know I'm going to get that exact same answer that I had in number 5. So again, I am going to focus on, not 56 at the end, plus 56. I'm going to focus on using this box or area model for multiplication because I just think it keeps things more organized. But don't be surprised if you hear this distributive property or FOIL mentioned by teachers in the future, or if you're like, hey, Mrs. P, that makes sense. You are welcome to do this as well. So we're going to do just a couple more problems together. I think I had mentioned previously when we were talking about quadratics in one of the videos is how do you get from this vertex form that shows you the transformations? We know this x plus 3 because it's in parentheses. This would be left 3. And the plus 5 at the end is up 5. So I know I have a parabola that has moved to the left 3 spots, its vertex, and then it's moved up 5, 3, 4, 5. I should have moved this graph a little over, but I know I have a parabola that looks something like this. So I know it's not going to have any x-intercepts. It has no solutions, therefore. I know it's facing up because there's no negative in front. But I think I had mentioned that you can get from this vertex form to the standard form, the form that we use when we are solving using the quadratic formula. And to do that, we need to use this FOIL or this box method multiplication. Now you may be thinking, well, in number 8, there is no multiplication, but there is. Yes, we definitely have this addition right here. Sorry, that shadow is in the wrong spot. But think about what it means to square. Squaring something actually means multiplying something, in this case, x plus 3. Squaring means multiplying it by itself. So we do have multiplication in this problem right here. Now we still have this plus 5 at the end, so we can't forget about it, but squaring means multiplying something by itself, which then also makes sense why x times itself is x squared. Now, just because of lack of room, you know what? I'm going to go ahead and do this FOIL method one more time for those of you who do prefer this over the box method, and then I'll go back to the box method. So for me to multiply, I'm going to ignore the 5 because it's not part of the multiplication. It's added on at the end. I'm going to do F first. So I'm going to multiply my x times x because it's the first term in each parenthesis, and that gives me x squared. O for outer, so that's going to be my x times 3, which is 3x. Now you might be able to see, some of you, why this is also, FOIL is also called the distributive property, because I'm distributing that x to everything in the following parenthesis. Moving to I, inner, that'll be my 3 times x. And L last, that'll be my 3 times 3, which is 9. And again, for those of you who are seeing why it's also called distributive property, I distributed the x to everything in the next parenthesis. I distributed the 3 to everything in the next parenthesis. The acronym FOIL just helps keep that distribution it helps keep a good order to that distribution. So like before, like every other example, now I'm going to look to add as much as possible. The only place I can add is the 3x plus 3x, which is 6x. I'm going to bring down the x squared. And oh wait, don't forget, we have this 5 up here that wasn't part of the multiplication, which means we do have a little bit more addition we can do. 9 plus 5 is 14. So this function up here is exactly the same as this function down here. This one just happens to be in that standard form, that form that we use if we're going to solve using the quadratic formula. So now I have my A, which is 1, my B, which is 6, my C, which is 14. And this form is just my vertex form. It's the form that helps me identify things about my graph. It's how I knew that this parabola was going to be left 3 and up 5 without having to actually graph in my calculator. So for those of you wondering, how do I get from that vertex form, that transformation form, to that standard quadratic formula form? That's how. It's by performing this multiplication. So let's flip over to 327, do a couple more, and then we are going to I'm going to let you guys do some practice. So you'll notice I already have some boxes set up in here. And like we said over here, we call these polynomials because the term or the prefix poly literally means many. We are multiplying things that have many terms, many letters, many numbers in them. Now, as I said over here, in math, you're going to end up dealing with one term, two term, and three terms a lot. So they have their own names, which actually makes sense. If you think about riding a bike, when you first learned how to ride a bike, you probably learned how to ride a tricycle. We know the prefix tri means three. So I'm going to kind of make myself a note here. We know the prefix tri means three. So that means a trinomial means I have three terms. Trinomial is three terms. So x, one term, plus sign, y, second term, plus sign, z, third term. Three terms. This particular polynomial can be called a trinomial because it has three terms. Now this, since we're going to start with example C now, this says a trinomial times a binomial. After you learned how to ride a tricycle, you probably got those training wheels taken off, or you moved to your big kid bike and you rode a bicycle, which has two wheels. The prefix bi means two. So in this case, we are doing a three terms, a trinomial, times two terms, a binomial, the x and the 2. So as you can see, all of the terms are written out across the top and the side. If I had turned my box this way, I could have done the three terms down one side and two across the top. It's really up to you. And I'm going to multiply to fill it in. So here we go. X times x, x squared. X times y. Well, x and y are not the same variable, so kind of like doing 7 times x or 2 times x, we just write those next to each other. We're going to do the same thing with the xy. I'm just going to write them next to each other. Moving over again, we have x times z. Can't really multiply two separate letters, so I'm going to put them next to each other. I'm going to move to the bottom left. 2 times x is 2x. 2 times y is 2y. And 2 times z is 2z. Now, just because of space, you know what I am. Never mind. I'm going to write all of this out. We're not going to answer in the box. I'm going to write this all out, and we're going to look through to see how much addition can we actually do. Keeping in mind that in order to add, we have to have the same letter. So I see some x's. But I also have to have the same exponent, which is, oops, you can't see the end of that, which is why I cannot add together my x squared and my 2x, because although they both have x's, they don't have the same exponent. Although these terms have x's, they also have some other letters. So if I look around, there is nothing else that just has an x squared. There's nothing else that has an x and a y. There's nothing else that has an x and a z. Nothing else that's just an x. Nothing else that is just a y. Nothing else that is just a z, which means there's no adding we can do, which means we are done. We have multiplied this trinomial, these three terms, by this binomial, these two terms, and that is our final answer. Okay, so polynomial again means many terms. Specifically, if you have three terms, it's called a trinomial. If you have two terms, it's a binomial. Think tricycle, bicycle. Well, if you have one wheel, it's a unicycle. But that unfortunately does not mean we call it a uninomial. One term, it would make sense if it was a uninomial with my analogy here. One term is called a monomial. The prefix mono refers to one. So if I look here, we have one term x. Now, x didn't need its own set of parentheses around it for this multiplication because it's just one term. Those parentheses keep things together. If it makes you feel better, yes, you can place parentheses around that x. So a monomial, switch to a different color here, is going to be one term. And if I count here in this parenthesis x and then minus 8, that's two terms, which is our binomial. Now notice our box got a little bit smaller because there's nothing else that needs to be on x's side. It's the coolest part about the box. You can adjust it to be whatever size you need it to be. So we're going to multiply together. X times x, which is x squared, and x times negative 8, look at that minus sign, which is negative 8x. Now I'm going to take all of that out of my box. And by all of that, I mean the two terms that are there. And I notice that although they both have x's, they are not like terms. I cannot actually add them or combine them because one has no exponent, or technically an exponent of 1. The other has an exponent of 2. Can't add anything together. So we have completely multiplied our monomial and our binomial. So last example, we have a binomial, two terms, x and 3, times another binomial, x and 7. X plus 3 got placed across the top, x plus 7 down the side. I actually encourage you pause this one and do the multiplication on your own, and then unpause and see if it matches mine. So hopefully you tried this one. Here we go. X times x is going to be my x squared. X times 3 is my 3x. 7 times x is 7x. And 7 times 3 is 21. Now I'm going to take all of that out of my box because we never answer in a box. So you may be thinking, why do I know that there's a plus sign in front of the 3x? Why do I know there's a plus sign in front of the 7x? Why do I know there's a plus sign in front of the 21? Think about it this way. You don't walk around and say, I'm positive 14 years old. If you don't say negative, you assume by default it's a positive, hence the plus sign. This case, I'm going to look to see, is there any addition I can do? And I notice, I actually do have like terms. Both the 3 has just an x and the 7 has just an x, so I can gather them together. I have 10 total x's right there. And I'm going to bring down the 21. I'm going to bring down the x squared. And the result from multiplying my binomial times my binomial is x squared plus 10x plus 21. So actually, for one more thing, let's just practice with these prefixes and classify these polynomials. Can you count up how many terms they have and tell me, would you call it a monomial? Is it one term? Would you call it a binomial? Is it 2 terms? Or a trinomial, 3 terms? So let's look. 1 term, plus sign. 2 terms, plus sign. 3 terms. This answer happens to have 1, 2, 3 terms. So we would classify this answer as a trinomial. Okay. Looking at B, after we multiplied our 1 term by our 2 terms, our monomial by our binomial, our answer has 1 term, 2 terms. So our answer resulted in 2 terms, a binomial. And last but not least, we had multiplied a binomial times a trinomial. Our final answer is lots of terms. 1, 2, 3, 4, 5, 6. You'll notice we don't have any special word for 6 terms. So anything after 3, these just happen to be the special ones that you deal with more often. Anything after 3 just by default gets the name poly. It's got many terms. This is just simply a polynomial. Now, every time you multiply, do you need to also classify and give them a name? No, this is just practice right now because you will hear these terms later on in geometry next year, algebra 2 the following year. So just practice getting used to them. So at this point, I am going to have you all do some practice, which is outlined on Canvas. And I will see you again on Thursday, I think, right?